You have 5 database servers. You use modular hashing to distribute data. Server equals hash mod 5. Now you add a sixth server, hash mod 6. Almost every single key maps to a different server. You have to move 80% of your data. Consistent hashing fixes this. Add a server, move only 1/6 of the data. That is why every distributed database uses it. Consistent hashing. High-level design, day 12. Consistent hashing is a technique for distributing data across multiple nodes in a way that minimizes redistribution when nodes are added or removed. With traditional modular hashing, you compute hash of key mod n, where n is the number of servers. The problem is that when n changes, almost every key maps to a different server. If you go from 5 servers to 6, roughly 80% of keys need to move. This is catastrophic for a cache layer. Imagine your memcached cluster with 5 nodes holding millions of cached items. You add one node, and 80% of cache lookups become misses. Your database gets hammered with a cache stampede. Consistent hashing solves this by arranging the hash space in a ring, typically 0 to 2 to the 32 minus 1. Both servers and keys are hashed onto this ring. A key is assigned to the first server encountered when walking clockwise from the key's position on the ring. When you add a new server, it takes over a portion of the ring from its clockwise neighbor. Only the keys in that portion need to move. When you remove a server, its keys move to the next clockwise server. On average, when adding one server to n existing servers, only k divided by n keys need to move, where k is the total number of keys. This is dramatically better than modular hashing. Let me walk through how the hash ring works step by step. Start with an empty ring representing hash values from 0 to the maximum, arranged in a circle. Hash server A, and it lands at position 90 degrees. Hash server B, and it lands at 210 degrees. Hash server C lands at 330 degrees. Now hash a key called user:1, it lands at 150 degrees. Walking clockwise, the first server we hit is B at 210 degrees. So user:1 is stored on server B. Hash another key, order:42, it lands at 300 degrees. Walking clockwise, the first server is C at 330 degrees, so order:42 goes to server C. Now add server D at 60 degrees. Only the keys between 330 degrees and 60 degrees, which previously mapped to server A at 90 degrees, now map to server D. Every other key stays on its current server. That is the power of consistent hashing. Adding a server only affects the keys in the arc between the new server and its counterclockwise neighbor. Everything else is untouched. Basic consistent hashing has a problem. If servers are not evenly distributed on the ring, one server might own a much larger arc than others, creating a hotspot. With 3 servers, one might handle 60% of keys, while another handles 10%. Virtual nodes solve this. Instead of placing each physical server at one point on the ring, you place it at many points. Server A gets virtual nodes A0, A1, A2, up to A149. Each virtual node is hashed to a different position on the ring. With 150 virtual nodes per physical server, the ring has hundreds of points, and the distribution becomes nearly uniform. When a key hashes to a position on the ring, it walks clockwise to the nearest virtual node and gets assigned to that virtual node's physical server. If you need to add a physical server, you add its virtual nodes to the ring. Each virtual node takes a small slice from its clockwise neighbor. Instead of one big chunk moving, many tiny chunks redistribute. This gives even better load balance and smoother rebalancing. The trade-off is memory. With 3 servers and 150 virtual nodes each, you store 450 ring entries. With 1,000 servers, you store 150,000. Let me show the implementation in Go. The consistent hash struct has a sorted slice of ring positions, a map from ring position to physical node name, the number of virtual nodes per physical node, and a mutex for thread safety. The add node method takes a physical node name and creates virtual nodes by hashing the node name concatenated with the virtual node index. Each hash result is added to the ring slice and the mapping. After adding all virtual nodes, the ring is sorted. The getNode method takes a key, hashes it, and performs a binary search on the sorted ring to find the first position greater than or equal to the key's hash. If the search wraps past the end, it returns the first position, completing the ring. It then looks up which physical node owns that ring position. The remove node method removes all virtual nodes for a given physical node and resorts the ring. The beauty is that binary search gives O log n lookup time, where n is the total number of virtual nodes. Adding or removing a node is O v log n, where v is the virtual node count. Consistent hashing is used in 4 major scenarios. First, distributed caches. Memcached and Redis clusters use consistent hashing to distribute keys across cache nodes. When a cache node fails, or you add capacity, only a fraction of keys are remapped, preventing a cache stampede. This is probably the most common use case. Second, database sharding. DynamoDB uses consistent hashing to distribute data across storage nodes. Cassandra uses it to assign data to nodes in the ring. When the cluster grows, data migration is minimal because each new node only takes a slice from its neighbors. Third, load balancing. Some load balancers use consistent hashing to route requests for the same session or resource to the same backend server. This is useful for sticky sessions or server-side caching. If a backend goes down, only its traffic redistributes. Other backends are unaffected. Fourth, content delivery networks. CDNs use consistent hashing to determine which edge server caches which content. When a new edge server comes online, it takes over a portion of content from its neighbors. Let me compare consistent hashing with alternatives. Modular hashing, hashmodn. Simple but terrible for scaling. Adding one server moves approximately 80% of data. Only acceptable for fixed-size clusters that never change. Rendezvous hashing, also called highest random weight hashing. For each key, compute a score for every server using a hash of the key plus server name. Assign the key to the server with the highest score. When a server is removed, each of its keys moves to the server with the next highest score. The advantage is no ring or virtual nodes needed. The disadvantage is ON lookup time per key because you hash against every server. Works well for small clusters, but does not scale to hundreds of servers. Consistent hashing with virtual nodes. O log n lookup via binary search. Excellent distribution with enough virtual nodes. Minimal redistribution on topology changes. Scales to thousands of servers. The standard choice for large distributed systems. Jump hash by Google. Extremely fast, near perfect distribution, zero memory usage. But it only supports appending servers. You cannot remove arbitrary servers. Used internally at Google for specific use cases. For general-purpose distributed systems, consistent hashing with virtual nodes is the industry standard. In system design interviews, consistent hashing comes up frequently. If asked to design a distributed cache, explain that you use consistent hashing to map keys to cache nodes. Draw the hash ring diagram. Show how adding a node only moves 1/n of the keys. Mention virtual nodes for even distribution. If asked about database sharding, explain how consistent hashing determines which shard owns a key. When the cluster grows, new shards take a portion of data from neighbors. Minimal data migration compared to modular hashing. A common follow-up is what happens when a node fails. With consistent hashing, the failed node's keys automatically map to the next clockwise node. Combined with replication where each key is copied to the next 2 or 3 clockwise nodes, the system remains available. Another follow-up is how to handle hotspots. Even with virtual nodes, some keys are accessed far more than others. Solutions include caching hot keys separately, splitting hot partitions, or adding read replicas for popular data. Always mention the trade-off. Consistent hashing adds complexity compared to simple modular hashing. You need to maintain the ring, handle ring updates atomically, and manage virtual node mappings. Only use it when your cluster size actually changes. 5 things to remember. Consistent hashing arranges the hash space in a ring. Keys map to the nearest clockwise server. Adding or removing a server only redistributes 1/n of the keys. Far better than modular hashing, which redistributes nearly everything. Virtual nodes are essential. Each physical server gets many ring positions for even distribution. 150 virtual nodes per server is a common starting point. This prevents hotspots and ensures smooth rebalancing. Used everywhere in distributed systems. DynamoDB, Cassandra, Memcached, Redis cluster, CDNs, and load balancers All rely on consistent hashing for data distribution. Implementation is straightforward. A sorted array of hash positions plus a map from position to node. Lookup is O log n via binary search. Efficient and easy to implement. In interviews, always draw the ring diagram. Show the before and after of adding a node. Mention virtual nodes. Discuss the trade-off versus modular hashing and rendezvous hashing.